Hello and welcome to the HyperXtract application. This is a two-part video. In part 1, we will discuss file loading and event extraction. In part 2, we will discuss event fitting and other analysis tools available in the HyperXtract software. This application allows you to extract and analyze events from your nanoboard traces. This application is compatible with 3 file types, namely the ABF files from the Clampex software, ABF files from the Eager Pro, and the DAC binary files that are generated using LabVIEW. The status button indicates whether the program is busy or not. Yellow or magenta means busy, green means available. After selecting the correct file type, click the Select and Load File button and then click on the file that you wish to analyze. If the incorrect file type is chosen, an error will be yielded. Once you select and load the file, you will see trace attributes getting updated, for example, the sampling rate and the input current unit. It is also recommended to verify that the correct input current units are picked up by the application. The unit can be selected to be picked up from the header, estimated based on the current, or entered manually. You will also have to choose the event type. They can be resistive, conductive, or biphasic. We will look at the biphasic events in a little bit. Under File Attributes, you can see the file information corresponding to the chosen file. If a binary file from a LabVIEW origin is chosen, the program expects to have a text file accompanied by this binary file. Information about these files can be found in the Compatible File Types document included with the HyperXtract application. The controls within the file attributes include precision, bytes per reading, data scaling factor, signal channel, header offset, data channels, endianness, and instrument string. More information about the instrument string can be found in the Compatible File Types document. The signal channel is important for multi-channel files. By default, we expect the current to be in channel number 1. If this is not the case, this should be updated. The No DDC stands for No Data Type Conversion. If you change any of the file attributes, please click the Update FATA button to update your selections. Now, let's look at the Biphasic Event tab. Before we go through the fields in the Biphasic Events tab, let's load a file that contains some biphasic events. I'm going to click TestEDT, and that displays a segment of the trace. We're going to look at what TestEDT stands for later. I'm going to zoom in on one event. It's going to be a randomly chosen event, and we can see that in this particular event, the first pulse, or the leading pulse, is conductive in nature, and the trailing pulse, or the pulse that follows the leading pulse, is resistive in nature. What we do is set the leading pulse to be conductive and the trailing pulse to be resistive. Because the leading pulse seems to have a higher magnitude throughout the trace, we're going to set the leading pulse as the main extraction pulse. The exponential endpoint adjustment accounts for fluctuating baselines on either side of the event and adjusts the boundary points using the Find Change Points function of MATLAB. Please refer to the SI of the paper titled Gateway to Data Visualization and Analysis in Solid-State Nanopores for more information. The program will initially extract the leading pulse. To find whether it is a true biphasic event or not, we need to scan a few milliseconds after the leading pulse. That can be done using the ScanAhead millisecond function. We're basically asking the program to scan these many milliseconds after the leading pulse to find whether there is evidence for a trailing pulse. If the situation has reversed, where the main extraction pulse is the trailing pulse, we have to tell the program to scan back to find evidence for a leading pulse, which will make the event a biphasic one. Typically, we do the scanning to find evidence for the biphasic nature for about 20 milliseconds, but this can change depending on the molecule and the event characteristics. The step size is a field used for baseline correction. It is typically set to 200. The Gaussian event smoothing is also an associated field for this baseline tracking system. The event detection threshold, or the EDT, of the primary pulse is set using the Event Thresholds tab, under which you can find the EDT for the primary pulse. The secondary EDT is set using the secondary pulse EDT, which is the trailing pulse for this biphasic event. Let's load a file with no biphasic events. Now let's look at the Trace Boundaries tab. It contains critical information about the boundaries of the trace, for example, the length of the trace in seconds, the start time, and the end time in seconds. These define the boundaries within which you want to perform the analysis. The maximum events per window basically determines how many events the program will extract for a given window size. The window size can be found under the Extraction Thresholds tab. If multiple files are selected, the file number option will become available, and you can toggle between the files. This is useful when you're testing the EDT. Let's look at the Core Baseline tab. This is an option designed for a better estimate of the mean and the standard deviation of the baseline. The working principle of this option is as follows. If the data was recorded at a rate higher than that defined by resampling threshold field, the data is downsampled to the rate defined by resampling threshold field. The trace is then histogrammed and smoothened using the smooth points field. The program then looks for prominent peaks. These represent the most common signal levels. There are two possible scenarios. One clear peak. The baseline is centered on one prominent peak. The program then keeps points within 3 standard deviations of it. Everything else is probably a spike or event. Multiple peaks. Program looks at how fast the signal is changing. Points where the signal changes rapidly are flagged as events and thrown out. What's left is the baseline. From the surviving baseline points, the program computes the mean and standard deviation. If calculations fail in any of these steps, program defaults to using the mean and standard deviation of the whole raw signal within the analysis window. The first capacitive time should only be used if there is evidence for capacitive-like current structures at the beginning of the file. The program will ignore the time segment defined by the capacitive time in milliseconds and would not take that segment into account for the analysis. Now let's go to the Adaptive Baseline tab. In it, you can find the Auxiliary Baseline Fitting radio button. If you click it, the baseline options become enabled. These options are to be used depending on the severity of the baseline drift of the trace. More information about these options can be found in the paper corresponding to the Event Pro app. Now let's look at the Extraction Thresholds tab. The window size in seconds determines the segment size that is taken for analysis. By default, it is set to 0.5 seconds, meaning segments that are 0.5 seconds long are used to extract events. The EDT stands for the Event Detection Threshold. The EDT type can either be based on the standard deviation of the baseline or, depending on the delta I, EDT start can either be from the mean of the baseline or from the edge of the baseline. The Test EDT allows you to test the event detection threshold, and you can ask the program to show low-pass filtered and unfiltered EDT by clicking the Show Filtered and Unfiltered EDT radio button. Now, before you click the Test EDT, you want to adjust the start and end time within which you want to view the EDT. Because we are analyzing the file in chunks of 0.5 seconds, it is recommended that the segment length for the EDT is also of comparable size. We are going to set the start time to 5 and the end time to 5.5 seconds and click Test EDT. Now you can see 3 lines appearing. The cyan line corresponds to the baseline mean, and if you turn on the Remove Events radio button on the core baseline, you would see magenta-looking points appearing. These points correspond to the isolated baseline. If these magenta points radiate into the event-like structures, that means the remove events is not taking place efficiently. Therefore, you have to change the parameters within the core baseline tab. The red line correspond to the EDT line. Any spike deeper than the red line are considered to be events. Now let's look at the filtering tab. It contains options to low-pass filter the trace. To enable low-pass filtering, click the Low-Pass Filter Trace radio button and a host of options will become available. LPF stands for Low-Pass Filter. You can set the LPF in kilohertz. For the LPF type, there are several options available. Depending on the type you have chosen, the ripple lengths and stop bands will become enabled. For the LPF method, there are 2 methods, the fast method and the better method. We recommend the better method. The SM rate stands for speed mode rate. This essentially downsamples the trace. To enable this, click the Speed Mode button. This is most useful for megahertz level data acquisitions if you want to get quick feedback on the events, but you also run into event distortions through this option, so it is not recommended for final analysis. Now let's go to the Other Parameters tab. In it, you find the event padding, which is the number of data points you want to leave on either side of the event after the extraction. This could be in milliseconds or in the number of data points. There is also the back step. After finding the deepest location of the event, the program works its way on either side of the event to find the event boundaries. It does this until it hits the threshold that is defined by the product of the backstep and the window mean. For example, if the backstep is 0.999, then the threshold becomes 0.999 times the window mean. Now let's look at the Parallel Computing tab. In here, you can activate the parallel computing capabilities. Before doing so, it is recommended to check whether parallel computing is turned on. You can do that by clicking the Parallel Status button. Right now, it says active. If it says not active, click Initiate Parallels and the parallel computing will be activated. To shut down parallel computing, click Shut Down Parallels. You can also change the number of workers to be active. By default, it uses the maximum available number of workers. If you want to use a different number, click the Use Default Workers radio button and input the number of workers to be used under the Workers to Use field. If we go to the Parameter Overview tab, we can see a selected subset of the parameters in the Main Parameters tab listed in this text window. If you update any of the main parameters, be sure to click Refresh Overview to get an updated view. Now, if you are satisfied with all the parameters, click the Extract button. Parallel Extract only becomes active if parallel computing is active, otherwise, it will yield an error. You can see the progress percentage in the Progress Percentage field. This is not active for parallel extraction. Once the extraction is completed, the number of events and the evaluation time will be displayed under Event Counter and Evaluation Time. If for some reason you want to stop the analysis, click the Stop button. Note, it does not work with parallel extraction. Once the events are extracted, we can go to Event Population Refining and Histogram if there is a need to refine the events further. In this tab, the user can histogram the extracted data. Histogram options are provided in the drop-down menu, and binning rules are provided in the Binning Rule drop-down menu. The bins can also be set manually by clicking Manual Bins. If you click Plot Histogram, the histogram corresponding to the parameter of interest will appear. If you want to fit the histogram, click the Perform Fitting and Overlay on Histograms radio button. Then the Fit Model drop-down menu becomes active, from which you can choose the model of interest. In this case, we are going to choose the single Gaussian option. Before we fit, we need to estimate the seed values. These are the initial guesses the software will use for the fit. Once we click Estimate Seed, we can see the seed values appearing in these fields, and then we can click Plot Histogram. In this instance, we can not only see the histogram, but we can also see the fit line. Since the single Gaussian seemed to be not a good fit, let's change the model to GMM. The normalization method has to be changed to PDF for GMM fitting method. Let's enter 2 for the field P, which stands for number of populations. Let's plot the histogram. The fit looks better. There are 2 options that are grayed out in the Data Fitting tab, X in log and Forced X cutoff. X in log becomes active when we choose the log normal option. In the log normal option, if the X data is already in log scale, click the X in log radio button. Otherwise, the program will convert the data into log scale. The Forced X cutoff becomes active when the exponential tail option is chosen. If you click Forced X cutoff, you will see a field appearing with the label X. Here, the program essentially eliminates any data points below the bin defined by the field X or bin with the highest counts. After you estimate the seed using the Estimate Seed button, you can plot the histogram with the model of interest. If you go to the Fit Overview tab, you can find the fit details. Navigate to the Rejection Thresholds. This table can be used to filter events. You can set a minimum and a maximum and then reject events based on these levels. You can make each of them active or deactivate them. Once you are satisfied with the rejection boundaries, you can click View Filtered to view the filtered distribution. Click Display Removed radio button to view events that are removed using the detection thresholds. These will be displayed in red. If you want to replace the existing parameter file after the removal of the rejected events, click Replace Original Parameter File. This also temporarily removes the daughter file and event location file from the program. If for some reason you feel like the event removal is not as good as you thought and you want to retrieve the original, click Retrieve Original Parameter File. This calls back the original daughter file and the event location file. You can also see the number of events removed and retained using these fields over here. You can also change the plot limits by deselecting Auto Plot Limits and setting your own. If you want to retain the limits for the next file, click Retain Limits. Otherwise, the limits will be zeroed and reset when a new file is loaded or when extraction is done again. To view event rate, navigate to the Event Rate tab and click Plot button. The event rate is displayed as fit rate per second. This option is not available for multiple file loading. Now let's go back to the Extraction Progress tab and navigate to the Scatter Plot tab. In here, you can plot your scatter plot either as a single color or as a color-weighted plot. If you want to keep your plot limits the same for the next file, click the Hold Limit settings. Otherwise, when a new file is loaded, the plot limits will be automatically updated. Click on Plot Scatter to view the scatter plot. If you want to save your current configuration, go to the Settings tab and click Save Extraction Settings. Conversely, if you want to load a particular set of pre-configured extraction parameters, click Load Extraction Settings. Then navigate to the Data Saving tab and click Save Trace Data button. This creates the .bin daughter file and the event location file. 2. Event validation and the false log. Now that we have extracted events, you can review them. If you identify a false event, you can add it to the false event table on the right. If you want to remove a particular event from the false log, use the corresponding buttons. These functions also operate through keyboard shortcuts. Control plus right, next event. Control plus left, previous event. Control plus up, add to false log. Control plus down, remove from false log. After reviewing, if you have any events in the false log, click Save Trace and Parameters. This will update the data file and the Excel files previously saved for the loaded file. The details of the event currently being viewed are displayed under the Event Details text area. The total number of false events and the number of events being saved are displayed here as well. If you want to clear the false log completely, click the Clear False Log button. 3. Concatenated View and Data Loading. The software also has an option for you to view concatenated events, in other words, events that are strung together. Navigate to the Concatenated View row tab. There are two subtabs, Data Loading and Data Viewing. Under Data Loading, you will see two file fields, the binary data file and the event location file. The .bin daughter file goes into the binary data file field, and the event location file, which is generated during the initial event extraction, goes into the event location file field. If you already have these two files and want to use the software simply as a viewing tool, click Load Concatenated Binary File and Load Event Log File respectively. 4. Data Viewing and Filtering. To view the events, go to the Data Viewing tab. The total event count is displayed under Total Events. You can view the concatenated traces by clicking the View Concatenated button. The Start Concatenated From field allows you to choose the starting event index, and the concatenation length tells the program how many events to display in a single window. You also have the option of low-pass filtering the concatenated trace. Simply click the Low-Pass Filter Concatenated Trace radio button and enter the frequency in the LPF kHz field. You can also change the colors of the events in the display using the two drop-down menus. By default, both are set to black. If we set Color 2 to magenta, you will see alternating events colored in magenta for easier identification. 5. Batch analysis and parallel computing. So far, we have discussed single file extraction. If you want to extract events from multiple files simultaneously, you can use the batch extraction capability. To do this, go to the Main tab and navigate to the Batch Analysis tab. Click the Select Multiple Files button and select the files you wish to analyze. Note that batch extraction is only possible when parallel computing is activated. Additionally, the sampling rate must be identical across all selected files. After selection, you will see the file name, length, start time, and end time appearing in the table below. You can manually change the start and end times to a desired range. By default, they are set from 0 until the end of the file. Once you have finalized your selection, click Parallel Batch Extract. It might take a few seconds for events to get extracted. The Auto Pick Settings radio button instructs the application to get the sampling rate and the current units from the header of the binary file. Once the extraction is complete, similar to the single file analysis, navigate to the Data Saving tab to create the daughter.bin file. This brings part 1 of the tutorial to an end. Thank you for watching.